So we've been doing math stuff, adding, subtracting, multiplying on matrices, and I hope after looking at all these different types of matrices, you've learned that matrices come in various shapes and sizes. We could have 2 by 4s, we could have 1 by 3s, so on and so forth. Today we're going to look at a particular attribute of matrices called a determinant. However, determinants are a property of square matrices. So just some vocab for us. A square matrix is a matrix that has the same number of rows as columns. Right? So they're matrices of equal length and width. A 1 by 1, a 2 by 2, a 3 by 3, so on and so forth are all square matrices. Now, if your matrix is square, they inherently have a property called a determinant. Now, what exactly is a determinant? That is really a question for sort of like pre-calculus or calculus and beyond. Geometrically, it has to do with like volumes of parallel pipe heads. For our purposes in Algebra 2, just think of a determinant as sort of an ID code. You know, when all computers have MAC addresses, all cars have VIN numbers, all iPhones, all your cell phones have a serial number. That's basically what a determinant is. It's just a unique number to that particular matrix. But the cool thing is you can do stuff, you can figure stuff out with that determinant. So today we're going to find determinants and do one small application of it, and then tomorrow we'll do another application of determinants. So how do we find determinants? It's true that determinants exist for all square matrices. We're only going to do 2 by 2s and 3 by 3s. Once you get into bigger matrices, 4 by 4, 5 by 5s, the math gets a little bit wicked. We'll just stay with 2 by 2s and 3 by 3s. So, determinants of a 2 by 2 matrix. Oh, shoot. Sorry. I'm going to have to make you erase. Let's talk about notation first. All right. I'm going to be writing a whole bunch of symbols, and you're going, what the heck does that mean? All right. Notation. Right. If we have matrix A, then its determinant is denoted by, determinants have many different notations. We can abbreviate DET parentheses A, or we can drop the parentheses altogether, or you can use vertical bars. Now I know in math, typically when we see vertical bars, we think of absolute value. If the context is matrices, that's not absolute value, that is determinant. Right? You don't have to put the matrix name inside of those absolute value bar or into those vertical bars. If you were to put the whole matrix itself, right, that would also mean determinant. So for example, I'm just going to make something up. 2, 3, 5, 9. See how we use a square? We use those square brackets. This is a matrix. If I were to change those square brackets into vertical lines, this is a determinant. So just be careful of your notation. If you mean a matrix, make sure you use a square bracket. If you mean determinant, you do a vertical line. I can't tell you how often I have in the past students going, hey, find the determinant of 2, 3, 5, 9. So they write this, and I'm going, that's not a determinant, and they start arguing with me. So it's just a little nitpicky notation. If you're going to talk about determinants, use vertical lines. If you're going to talk about a matrix, use a square bracket. Question?
So if you had -3, 2, 5, 9, the determinant would be positive 2, 3, 5, 9?
So the question was, what if it was negative? So what if I had like -3 and -5 here? If I wanted to denote the determinant, it's still like that. Again, these are not absolute value bars, so this is not 2, 3, 5, 9. Those guys are two different things, right? So determinants are not absolute values. You could get negatives in them. Right? Good question. So let's go ahead and talk about how we find them. So determinant of a 2 by 2. I'll first write down the definition, and then I'll show you sort of the visual interpretation, the visual shortcut. So, if matrix A is a 2 by 2 matrix filled with random numbers, I'll just use A, B, C, D. All right, they stand for random numbers. Then, the determinant of matrix A is this formula, AD minus BC. Now that seems like a random formula. Well, it does have a visual shortcut to it. If we take a look at the original matrix, AD is just this diagonal multiplied to each other. BC is just this diagonal multiplied each other. So when I do determinants, I sort of think of it as a crisscross and then you subtract. You multiply along the diagonals and then you subtract them. Easy peasy. Example, find the determinant of, throw out some numbers. 7, 9. Let's make it a negative and then a 5, I heard, right? Notice I did not use square brackets, I used vertical lines. So this, even though I don't use the word determinant, you need to know that this means determinant. Well, okay, I can follow the formula or just use that pattern. It's crisscross 7 times 5 minus the other diagonal, 9 times a negative 4. That's all a determinant is. You crisscross and then you subtract. So that's 35 minus a negative 36, which gives you a positive 71. The determinant is 71. Again, for right now, that number won't mean anything to you. A determinant is just a number that's unique to that matrix, but we'll talk about applications of it later. Not too bad, right? Pretty simple, easy peasy, crisscross, subtract. If we had fractions inside the matrix, you said, okay, sure. Let's do another example with fractions. It's the same concept. Fractions don't change anything. I'll change the instructions to make it look different. Find the determinant of A if A equals, I don't know, 2/3, -1, 5, -4/5. I don't know, I'm just making it up. Right. I could put fractions inside of it. It really doesn't change your work at all. So, okay, let's do this. The determinant of A equals crisscross. So this guy here, so that's 2/3 times -4/5 minus the other diagonal, -1 times 5. Just because we have fractions doesn't mean the math changes. So when you multiply fractions, you go straight across. That's -8/15 minus a -5. And then all you got to do is add and subtract fractions. Add and subtract fractions, common denominators, yada, yada, yada. Right. So for the -5, I need to multiply by 15/15 to get the common denominator. So that's -8/15 plus, and 15 times 5 is a 75. Right. And then you just go ahead and do math. That's a positive 67/15. Right, there you go. So whole numbers, fractions, negatives, it's the same crisscross subtract. Yep. We good? Yep. A 3 by 3, as we naturally expect. What's the difference between a 2 by 2 and a 3 by 3? Well, you have one extra column and one extra row. So not surprisingly, to find the determinant of a 3 by 3, you just have extra diagonals to crisscross. Now, instead of writing a formula, because it's going to have lots of letters, A, B, C, D, E, F, G, it's going to get too confusing. Please don't touch that. I think it'll be easier to showcase with just diving straight into an example. Right. So let's find the determinant find the determinant of, spew out some numbers. Remember, we're solving this, so keep it reasonable. 4, -2, 7, 3. Let's make that negative. 6, 1. Let's toss in a 0 and then a 9. Right. So if you had to find the determinant of a 3 by 3, this is the technique. First thing I'm going to do is I'm going to just rewrite it with the vertical bars because that's what determinant means. So everyone can do that, I hope. And what you do is you copy the first two columns on the right side. So here are the first two columns. I'm just going to rewrite them on the outside to the right. So we have a 4, 3, 1, -2, -5, 0. Step 1, copy the first two columns. Now notice with the 2 by 2, you know how it's the blue diagonal minus the yellow diagonal? We're going to do the same thing, blue minus yellow. But since it's a 3 by 3, instead of having 1 diagonals, we're going to have 3. So start the top left corner. You have 1 diagonal. You have 2 diagonals. You have 3 diagonals. You guys see that? Every single diagonal you multiply, but since they're all blue diagonals, we're going to add the answers together. So this is equal. Here's the first diagonal, 4 times -5 times 9, plus the second diagonal, -2 times 6 times 1, plus the third diagonal, 7 times 3 times 0. We're okay with that? Okay. I'm going to put square brackets just to group them together. And then just like with the 2 by 2, we're going to minus the yellow diagonals. Well, how do you start with the yellow diagonals? You start the bottom left corner. Here's one diagonal. Here's another diagonal. Here's another diagonal. And then just as before, within the diagonals you multiply. But since we have multiple diagonals, you're going to add them together. 1 times -5 times 7. Plus 0 times 6 times 4, plus 9 times 3 times -2. And just as with the blues, I want to group all the yellows together. That's it. That's how you find determinants. And then, of course, you do math and add and subtract and so on and so forth.
So the 3 and the -5, since they're not bubbled, does not matter?
So the question was, since this 3 here and this -5 was not bubbled, do they not matter? Yeah, I don't really do anything in terms of the calculations with them. Yep. Question?
So you have to rewrite on the outside to compensate for the ones that we left out?
So the question was, so we had to rewrite on the outside to compensate for the ones that were left out? Not necessarily. We had to rewrite them on the outside in order for us to get a full diagonal. Then notice if these outside numbers weren't here, I would not be able to do those outside diagonals. And then we just go ahead and do math, right? So what does this equal? So for the blue here, so 4, and then just break it out a calculator if you need it. 4 times -5 is -20, times 9 is -180. -2 times 6 times 1 is a -12. And 7 times 3 times 0 is 0. So that's pretty easy. -180 plus -112 is -192. Minus, and then do the yellow. 1 times -5 times 7 is a -35. 0 times 6 times 4 is 0. 9 times 3 times -2 is a -54. And then you just go ahead and add those together. So that gives you a -89. And then you just do math. -192 minus a -89. That's -192 plus 89. What is that? Carry the 1. Is that -103?
Yeah.
-103. That's the determinant.
What about if you have, wait, is it always gonna be a negative, like when you do your determinants, is it always gonna be subtracting?
So the question was, when you do determinants, is it always subtracting? Yes. This middle guy here for determinants, 3 by 3 or 2 by 2 is always subtracting. Always. Always blue minus yellow, always. Question?
So if it were like a 4x4, would we do the same thing except we would take 3 rows?
So the question was, if it was a 4 by 4, would it be the same thing except we would take 3 rows of copy on the outside? The answer is no. This is actually not the proper way to find determinants. It's sort of like a trick. It's sort of like a shortcut. If you are interested in knowing the, quote, proper way to do this, it's called cofactor expansion. Talk to me after the lesson, and I will gladly show you. It's a pretty cool way of doing things. But for a 4x4, it is a lot messier than this, so that's why I'm not going to touch a 4x4. But I'll show you after the lesson. Yeah. Any other questions? Are we good with the 3x3s, or do you guys need another example? Okay. So again, for algebra 2, right? This topic here is more for linear algebra. These numbers don't really mean much to you. They do have applications. They do let you do things. So we're only going to talk about the easy peasy applications. One application you can use determinants for is to calculate areas of triangles. You're probably going, wait, that's a geometry thing. I already know how to calculate a triangle. That's 1/2 base times height. But, what if you don't have a right triangle? You got to use trig, and sometimes trig is messy. Or what if your triangle is like miles away? What if you're trying to survey an area on a map? Determinants, math is a way to do it. So application.
Like coordinates?
Like coordinates, yes. Application of determinants. One application is area of a triangle. So let's pretend that you're analyzing a map and you want to find a triangular area, but we're talking about a map. Like, what if you want to find areas between states and stuff? Well, if you know the coordinates of the vertices, you can use determinants to find the area. So here's the idea. The area of a triangle with vertices x sub 1, comma, y sub 1, x sub 2, comma, y sub 2, x sub 3, comma, y sub 3 can be found by area equals plus or minus, and I'll explain the plus or minus later, 1/2 times the determinant. And what you do is you just put the points in the matrix. X sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3. You just list them down. That's pretty easy. But here's a problem. Determinants are only for square matrices. This is not square. This is a 3 by 2. I'm missing one more column. So all you got to do is fill that last column with 1s. Now, why is this plus or minus business? I hope you guys saw or realize or recognize. I'm going to scroll back down here, but let's take a look. Our first two examples, the determinants were positive. Positive 71. Oops. Come on. Positive 71 and positive 67/15. The second example, the determinant was negative, negative 103. Determinants can be positive or negative. There's no rule against it. So if we're going to use a determinant to find an area, we all know that area can't be negative. So this plus or minus here is to use whatever makes your area positive. If you have a positive determinant, keep the positive. If you have a negative determinant, you're going to use a negative to make it positive. That's all that plus or minus means. So don't get too scared off about that plus or minus. Let's do a quick example. Find the area of a triangle with vertices A located at 5, 11, B located at 9, 2, C located at 1, comma 3. Now, you guys probably did these questions in geometry, right? Give you a couple of coordinates and then find the area. Back in geometry, you probably sketched it. I'm not going to draw tick marks. This is not going to be accurate. I'm just doing a rough sketch. And you probably plotted it. 511 is somewhere up here. 9-2 is somewhere down here. 1-3 is somewhere right here. You probably sketched it. You connected the dots. Maybe your geometry teacher had you put it on grid paper so you can count the squares. Or maybe you broke out a ruler, measured the height, measured the base, and did 1/2 base on site. And that's totally fine. That's a wonderful method of answering this question. But you know what? It all depends on how neat your points are. It all depends on how straight your lines are. It all depends on how well you measure. And that's a lot of room for error. Is there an exact way to figure it out? That's the job of a matrix. So let's do this. Area equals plus or minus 1/2. And then all I'm going to do is put those points in a matrix. 511, 9-2, 1-3. And then since I want him to be square, fill it with 1s. And then you just do what we did in the previous example. Copy the first 2 columns over. 511, 9-2, 1-3. And then go ahead and make your diagonals. I'm going to ignore. So this guy here, I'm going to ignore the plus or minus until the end. So I'm going to save him. So don't forget him. Let's just work with the determinants. So we have this diagonal, this diagonal, this diagonal. So we have 5 times 2 times 1 plus 11 times 1 times 1 plus 1 times 9 times 3. We minus the other diagonal. Start at the bottom left. This diagonal, this diagonal, this diagonal. 1 times 2 times 1 plus 3 times 1 times 5 plus 1 times 9 times 11. And then you just, that's it. That's the hardest part. Just compute math. So we have what? 10 here. 11, 27. We have 2, 15, 99. So we have 10 plus 11 is a 21, plus a 27 is a 48, minus 2 plus 15 is 17, plus a 99. Well, 90 plus 10 is 100. So 9 plus 7 is 16, so it's 116. And 48 minus 16. Say that again? It's not 32. I'm going to take your word for it. So negative 68. Yeah, negative 68. Good. Okay. Now, the common mistake I get when I give this question on a quiz or test to students is they get so hyped up. Yay, I solved it. They circle it and move on. Remember, this is not our final answer. All this work here, this negative 68, is just this guy here. We got to incorporate the plus or minus 1/2. So the answer is area equals. Now, my determinant is negative, right? My area needs to be positive. So I'm going to use a negative 1/2 of that answer. So the answer is a positive 34. Notice how they didn't give us units. We don't know if these are inches, feet, miles, whatever. So just use a generic unit squared. The area of that triangle, I can guarantee you to the exact precision, is 34 units squared. You probably would have gotten some small area if we did it by hand using geometry. So that's one of the powers or applications of determinants, finding areas. Question? Oh, that stands for units. Because it didn't give us inches, feet, miles, so I just generic units. Yeah. So, do I want units? If I'm talking about area, I want something squared, yes.
Yep. Why I didn't understand why you put the ones, aside the y1, y2,
Yeah.
y3. Why do that?
So before we have this, but we're using a determinant, right? And the determinant only works for square matrices. If I didn't have that there, this is not square. This is a 3x2. It needs to be a 3x3. So we fill in the last spots with 1s to make it a 3x3. Yep.
And my other question, you did a negative 1/2 because of the plus minus sign on the side.
I did so the question was, I used the negative 1/2 because of the plus or minus sign. Yes, because the plus or minus means you have to use whatever symbol, plus or minus, to make your final answer positive, because we're talking about areas. Since our previous work said the determinant was negative, we needed to choose a negative 1/2 to make the answer positive. Let's pretend that the determinant was a positive 68, then I would have used a positive 1/2, because I want to keep the answer positive. Yeah. Good questions. Any others? All right. So those are our 2 objectives for today. Just 2. Very simple day, I hope. Number 1, can we calculate determinants? And number 2, can we find areas of triangles? That is 3.9a.